Okay. Today I want to talk about not Newton diagrams, not Newton polygons as last time, but about Newton Polyhedra. And they were introduced in a very powerful way about, say, 30 years ago. And since then, it was 30 years ago.
By Newton?
Well, let me see. There were several people who did it almost simultaneously, and it was very interesting. And since then, they became simply the one of the main tools in a lot of fields. And by the way, I have that Arnold's book here, where he explains how to use it for such interesting things as, say, analogs of Maslov methods for very degenerate phase functions. Maslov method requires the second differential to be non-degenerate, but sometimes it is degenerate. For example, in mode conversion, it is degenerate. Nevertheless, there are ways to write asymptotics very nicely under these conditions. And what is very important that in all these cases, the Newton polyhedra proved to be quite useful, quite important, and actually very adequate to the problems discussed. I think this is the size of chalk we are left with. Okay. Well, but there are many of these. Okay. Let me try to describe what kind of problems I want to talk about. Imagine that I have polynomials in n variables. And how many polynomials? N polynomials. So the polynomials are in many variables. And I want to solve such systems of equations. These are systems of n equations with n variables. And definitely x's are supposed to be complex. Well, what can we say about the set of solutions? Definitely whatever we can say should depend upon two inputs. What are the inputs? What are the should depend upon one input, as a matter of fact. What are the coefficients? Okay? Well, if you know the coefficients, actually you cannot say too much about the set of solutions, because it is extremely difficult to say anything anything non-trivial about the set of solutions. So, but something nevertheless can be said. For example, since we have n equations with n unknowns, generically there would be finitely many solutions. But the word generically is very important, because if I have two equations of the sort the same equation repeated twice, definitely it has infinitely many solutions. But obviously this is a very degenerate case where two equations are the same. Or if I have these two equations, they have no solutions at all, because 0 is usually different from 1. And therefore, in degenerate cases, the rule of the thumb that anything can happen. But since in practical matters we do not say that we exactly know the coefficients, for example, we should assume that our system is generic, because the moment we are allowed to change coefficients a little bit, but unpredictably, we get a generic system. So, generically, the number of solutions of this system is finite, and there is Bézout theorem which says how many solutions there are. And it depends only upon the powers of these, upon the degrees of these polynomials. I don't remember actually the exact formula, but actually it is the product of the degrees. The product of degrees. I do not need this, so I did not. I could not find the formula handy. So let me just put it this way. Okay. So the idea behind the Newton polynomials is the following. Let us pretend that we only know whether coefficients are zero or not. And if they are not zero, which coefficients are zeros and which are not. And if they are non-zeros, we do not know anything else about them. Okay? Therefore, we can write it this way. The polynomial, I will put it, x means x1, x2, xn. X is in Cn. Is the sum of a, k, alpha, x, alpha. Alpha, sum of alpha belonging to support pk, and I will explain this. X alpha by definition is the following: x1 to the power alpha 1, xn to the power alpha n. So alpha is a multi-index. Alpha belongs to z plus n. It is a vector of integer coordinates, positive integer coordinates, non-negative integer coordinates. So x to the alpha means exactly this. Ak comes from the number of the polynomial. Alpha is says at which power does it stand.
Are you saying alphas are all non-zero here?
Not necessarily.
No, they could be.
They could be zero opposite. They are all non-negative for sure. They are integer and non-negative. By the way, integrality is not that important, but let us assume it. And since I assume that alpha is in the support, it is the definition of the support, ak alpha is not zero for any alpha in the support pk. Support means all powers at which coefficients are not zero. Support are all powers, and powers are multi-indices, or multi-indices are actually integer points in Rn, correct? At which coefficients are non-zero. So I think I have explained the notion of support and how support is related to the function. So if alpha is in the support, that means that x to the power alpha indeed enters this polynomial, meaning enters with non-zero coefficient. So the question is, what can I say about these solutions, say about the number of solutions, if the only thing I know is the supports? So I know about coefficients, whether they're zeros or not. And if they're not zeros, I do not have any further information about them. So the question we are going to discuss is the following. I want to understand how many solutions generically. Generically means I don't know nothing about coefficients. How many solutions can I have here? If I know only the supports of the polynomial, of the polynomials. Actually, it is not a very good question, because since I am considering such notion as support, that means I have chosen a system of coordinates. Because the moment I change the system of coordinates, I make it even a linear transformation of the coordinates. The support is changing a lot. So, please note that the whole problem is coordinate sensitive. Because the notion of the support is coordinate sensitive. Because if I change the coordinates, coefficients which used to be 0 may become non-zero, and vice versa. Okay? And for a lot of reasons, I'm interested not in all solutions, but in solutions such that none of the x's in this solution is 0. So actually I want x's to be in C star n. Star means complex numbers without 0. So I'm looking for the number of solutions such that none of its components is 0. If I am in 2 dimensions, if I have x1, x2, that means, well, I simply do not allow x1 or x2 to be 0, and I'm trying to count the number of such solutions. Problem seems to be hopeless, and it was hopeless until 30 years ago. And I want to tell something about the history. I simply happen to remember this history very well, because I was present when this history was being done. There is a very strong mathematician who is a former student of Arnold, whose name is Kushnirenko. And he came up, Kushnirenko. I'll try to write Kushnirenko. A very strong guy. And he came up with a very interesting result. Actually, he came up with a formula for the number of solutions of this equation, of this system. And it was just a thunder, because nobody could even anticipate that such formula could exist. But this paper was a very difficult paper. It was published in Invenciones. It is one of the 2 top journals in mathematics. A very difficult paper with a lot of interesting techniques, with a lot of interesting ideas. Very difficult. And Kushnirenko was giving a talk at the Gelfand's seminar. And Gelfand was listening very carefully. They said, okay, this result cannot be difficult. And explained very well why it should not be difficult. It is an Olympiad problem. Who is a good Olympiad problem solver here in this room? And there were several winners of international Olympiads present. He found one.
Yeah, but I only did the ski jump.
Yes, and he found one of them, David Bernstein, who 3 or 4 years ago got the first prize in the International Olympiad for high school students, and said, okay, by the next Monday you should have a proof along these lines. Wow, how can I? You can. And indeed, in a week, he had a full proof with all details, and it was published. It was one page. I will try to reproduce not the proof itself, but the ideas behind the proof, and the ideas are due to Gelfand, to no one else, but Gelfand understood it very well. And suddenly, this very difficult work by Kushnirenko became next to trivial. But actually, the result is so good, and it was extended so much that it is still one of the main pillars of modern, say, computational algebraic geometry. Okay, so the result I'm going to talk about is due to David Bernstein, or in Russian translation, Bernstein. He's in the United States for about 30 years, so he's Bernstein now, but I think he got out of mathematics for some strange reason. Hmm? Maybe. Actually, he is so smart that he could have been whatever he wanted. Okay. Before I start explaining, the explanation is not quite easy. Before I start explaining, I want to consider the simplest case. What is the simplest case? N equals 1. So I have one equation. Well, it is too easy for us. It is, we have one variable and one polynomial. And let me write it this way. ASXS plus AS plus 1 XS plus 1 AN XN. And in order to be non-trivial, I assume that AS and AN are not zeros. I start with the smallest power, which is really present, and then
So it's not the original.
it is a particular case when n is 1. We have one polynomial of one variable. One polynomial of one variable. Okay. What is the support of P1? It is definitely a part of one line. The support are all powers at which the coefficients are definitely not zeros. And at least it contains the point S on the line.
Can I stop you? Why do the coefficients have to be real?
They're not necessarily real. Well, these are the powers that are real. Powers are real. And there is N. These two guys are definitely in the support. Maybe there is something else between them, but these are. So actually I do not know the support itself, but I at least know the convex hull of the support. And the convex hull of the support, should I explain what convex hull is? Yes, I will. Is called the Newton Polyhedron of the polynomial. Convex hull is the following. A set is called convex if it has the following properties. Given any 2 points in the set, the segment joining these points is also in the set. So tell me please, is this room, interior of this room, a convex set? Not. It has these awful columns, and if I choose a point on one side of the column and on the other side and try to join them, I will crash the wall. Is the interior of this cup convex? Yes, it is.
No, because there's a little, it goes down like this. this.
Okay. Okay, I understand. If the interior above the coffee, convex?
That's convex.
Yes, it is convex. Okay. Difficult to cheat you again. Okay. Now, if you have several points or infinitely many points in space, you can consider all convex sets which contain these points. For example, we can consider a huge ball which encompasses them all. It is a convex set, and so the convex hull is the smallest convex set containing the convex hull of a set is the smallest convex set containing this set.
Is it always defined with
Say it.
defined with respect to Euclidean
Euclidean what?
lines?
Sure, the lines are Euclidean. We are in the linear space. You see, we are living, convexity is defined for linear spaces. Because the notion of a segment joining two, definitely you can think about, say, some Riemannian surface, and instead of straight line, you can connect them by geodesics. But we're not talking about this kind of things. We are living in a linear space, as all law-abiding citizens should, and all our convexity is about a linear space. So, do we understand that this segment is the convex hull of the support? Because everything that is in the support is between these 2 points. And everything inside is automatically included. Okay. Very good. Now, tell me please, how many non-zero solutions does this equation have? Non-zero complex solutions. Very easy. All in all, it has n solutions, does it? But s solutions are zeros. So how many non-zero solutions? N minus s. Trivial. Senior kindergarten. For some strange reason, this happens to be the length of the Newton polygon. Is it? And this is going to be the general result. The number of solutions is going to be what is called mixed volume. There are several Newton polygons involved there, of these Newton polygons. But I have to explain a lot of things. What are Newton polygons? Newton polyhedra in the general case, it is easy. What is mixed volume? Something invented by Minkowski. And he did not invent anything trivial. And why this is true. According to Gelfand, why this is trivially true. But at least in this simplest case, we've got the result, have we? Okay, let me see. Okay, now let me shift to the case n greater than 1. Case n equal 1 is well understood. And let me shift further. On our way there, we will have to learn such things as K functor of Grothendieck and several other things. Okay, so now we have polynomials P1, P2, Pn, polynomials with complex coefficients of x1, xn. This is the usual way to denote the set of polynomials with complex coefficients. Actually, complexity is not important. But since we do not care about any other algebraically closed field by the complex field, it's okay. So again, support pk is the set of alpha in Z plus n such that, if you wish, okay, d alpha pk of 0 is not 0. This derivative is the coefficient of this polynomial. Say it again? You have to get the coefficient, you have to divide by alpha factorial, but if it is not 0, it doesn't matter. Okay, now the Newton polyhedron of pk is the convex hull or the support of pk. It is indeed a polyhedron with vertices at integer points. So it's better to understand, to do an example, simple example. Say P is, say, x1 plus x1 x2 cubed minus 5 x2 squared, for example, this. What is the support? Here the power is 1, 0, correct? Here the power is 1, 3. And here the power is 0, 2. So the support consists of 3 points. Let me add something, for example, x1, x2. x1, x2, I am adding this point. This is the support. Support consists of 4 points now. What is the Newton polygon? Newton, in this case it is a polygon, but Newton polyhedron. I must take this triangle. It is the convex hull of these 4 points. It is the smallest convex set, including these 4 points. As you see, this point is not very important. The convex hull could have been the same without this point. And coefficients are not important if I have put pi here or square root of the Avogadro number. It doesn't matter. Okay. So these are easily computed geometric objects, are they? The moment you get a polynomial, any computer can immediately compute its convex hull, not a big deal. And what is important, that this convex polyhedron contains a lot of information about the polynomial, a lot of important information. But first we need to do something, and please write down the heading: space of convex bodies. Okay.
You said that the length of the convex hull will give the number of solutions?
Not the length, but the volume, because if we are, and the, not simply volume, but the mixed volume, and I will explain. There's a long way to go.
I'm just kind of curious, though, whenever you have these kinds of, so if you have terms where you just threw on a term on the boundary of the convex hull, is that going to introduce like a degeneracy, like so that various families of solutions where you can add extra terms, but as long as they go on the boundary of the convex hull,
It doesn't matter. It does not change the number. Yes. Okay. I'm going to consider this set conv n of convex bodies in the n-dimensional space. The space of convex bodies in the n-dimensional space. So we are non-convex bodies in the three-dimensional space. After a good dinner, some of us at least can become convex. Most probably. Sometimes I do become convex. Okay. I want to introduce some operations with convex bodies. So let U and V be convex bodies. What is U plus V? I want to learn how to add convex bodies. It is the set of x's in Rn such that there exist U in U, V in V, such that x is U plus V. Simply take one vector from one body, one vector from another body, add them up, and everything you can get adding them up forms an U set U plus V. Definitely one has to prove that U plus V is convex. Homework. Prove that U plus V is convex. Couple of simple exercises. 0 is the convex body consisting of 1.0. Nothing else. Is it a convex? Yes, it is a convex body. Yes. If I add U plus 0, what do I get? U. That's good. So with respect to this addition, this is 0 for this neutral element for this addition. Then definitely U plus V equals V plus U, because the order is not important. Next, U plus V, I have to prove that this is a convex body. It is not a big deal, but simply you need to use the definition of convexity. And plus W is U plus V plus W. Also, not a great surprise, because what I have to do is simply to add U plus V plus U small plus V small plus W small, and this does not depend upon how you add them. So far, so good. What else? Nothing. So, one thing more. What is U plus U?
Necessarily contain 0.
Not necessarily.
I'm going to stop and ask that myself. I think 0. And this,
0, not necessarily.
and this is ordinary vector addition.
Yes, ordinary vector addition. U plus U. The idea is that this is 2U, but 2U in a different sense. 2U, you take every vector and simply stretch it 2 times. Again, you have to prove it. It's not a big deal. So vector addition is well connected with homotheity, with simply expanding with respect to 0. So what I want you to do is to prove that this is convex and this is indeed true. It is not a big deal, but it is a very good exercise. If you can do it in 2 dimensions, you can do it in any dimension. So my suggestion would be try to do it in 2 dimensions, and then convexity is going to be quite important. Now, let me go further. So the set conv n is a semigroup. You can add, you have neutral element, but what you cannot do still? Subtract. And subtraction is impossible. Why? Subtraction, the simplest subtraction is my attempt to solve this equation. Correct? That means I look for some convex set so that I add it to U, and what I get 1 point, 0. If my convex set is not 1 point set, it is impossible. So, the first bad thing that happens is that subtraction is impossible. Subtraction is impossible. But if it is impossible, but we want it badly, we have to invent a way to subtract. And the way to subtract is k-functor by Grothendieck. But frankly speaking, it was known to humankind, say 3,000–4,000 years before Grothendieck, and in a special case. But Grothendieck understood that this is an absolutely crucial piece of construction. Yes, there was the first, as a matter of fact, the first tablets were devoted entirely to k-functor. So you understand that it was written over there and contained the name of Grothendieck. Okay. Let me explain how people knew about k-functor long before Grothendieck. Attention, please. Consider positive numbers, strictly positive, without 0. Strictly positive numbers, integer numbers. We know how to multiply them, do we? Take any 2 integers, multiply them, you will get an integer. We know the neutral element, what is it? It is 1. 1 multiplied by anything is. So, this set is a semigroup with respect to multiplication, semigroup with a neutral element. But the moment we want to divide, we are in trouble. There is no integer number such that multiplied by 5 it will give 1. So, impossible to divide. So what did we do? We introduced, not we, but people who wrote the tablets introduced the ratios or the fractions. What is a fraction? A over b. We write it this way. But actually the fraction is a pair. Is it? If you know A and B, you know a pair. But some pairs are pronounced to be the same, equal. So A1 over B1 equals A2 over B2. By definition, this means A1 B2 equals A2 B1. So, the pair A1, B1 is equivalent to the pair A2, B2. By definition, it means the following. Okay? And now we simply embed z plus into z plus squared into this set of pairs as follows. A goes to A1. I will put it modulo this equivalence relation. So I take Z2, but some pairs are pronounced to be equal. So I take a, and in this case I should take the equivalence class of this pair. So this is called Q plus the set of pairs with this equivalence, the set of equivalence classes of pairs with this equivalence relation is called the set of positive rational numbers. Correct? And in rational numbers we can divide. So we were able to take a semigroup and embed it into a group, because positive rational numbers form a group. We can divide. Correct? Embed it into a group. And this is called the Grothendieck K-functor. When you have a semigroup with some condition, and I will discuss this condition, please write it this way. You take a group with a cancellation condition, and I will discuss it. And Grothendieck's functor constructs a group into which this semigroup is embedded. And when you are in a group, then you can, in this case, divide. In our case, we will be able to subtract. But the objects will be no longer convex sets, but something else. So actually, K-theory is one of the most important theories in modern mathematics, because this K-functor and its various analogues are needed in practically any reasonable field of mathematics and of physics now. So let me try to reproduce the same kind of reasoning in our case. So I consider convex n times convex n.
Where's the K? What's K? Why call it K?
Difficult question.
Is it German or Dutch?
Grothendieck is, well, that's a difficult question. His name is a Dutch name, but his father was one of the closest people closest to Trotsky. He was a revolutionary who was killed in some skirmishes in Germany in the 20s. His mother took him to, it was a Jewish family, they took him to France, and during the German occupation they lived in France, in somewhere in the south, and they had to hide from, because every now and then Nazis will come to look for Jews, and they would be taken to some Catholic monastery in the hills, and he would stay there for some time, then return back to a small city. So Where K comes from, I don't know, but the origins of Grothendieck are these. He is probably the greatest mathematician of the 20th century. Unfortunately, he is very sick. He is alive.
You're not saying greater than Hilbert, you're saying greatest living.
Well, maybe quite comparable to Hilbert. He simply changed the face of mathematics in a way that maybe no one else did. But he is also was very politically active. For example, he refused to come to Moscow, where there was Congress, where he got his Fields Prize. He refused to. Then he refused Crawford Prize, which is the closest Nobel Prize for mathematics. He refused to accept it. Actually, he is very sick. He is mentally ill, and he is living somewhere in a small village in Pyrenees. So it is an awful situation that a person of such. He left mathematics at the age of 41 or 42. Everything he did was before that. And his legacy is, say, 20,000 pages of first-class mathematics. 20,000.
Is this an argument against learning mathematics?
Maybe. Actually, a lot of mathematicians were very irritated by him writing huge books, because what he was writing was supposed to be read. Otherwise, you are outside of the mainstream. But okay, let me not go further into this. So, consider convex pairs of convex sets. So, UV. And write it this way, U minus V. It is only the way to write it. Instead of writing two parentheses and a comma, I will write simply one minus between them. Nothing else. U minus V. Now, pair U1 V1 is equivalent to the pair U2 V2, and you can easily understand what does it mean. It must mean that this U1 minus V1 is equal to U2 minus V2, but this can be rewritten without minuses as U1 plus V2 equals U2 plus V1. Only addition, and addition is well defined. Now consider convex with this equivalence relation. So consider the classes of equivalence with respect to this relation. And let me call it K of this. I want to show that this is a group. And in the process of showing it, I will come across the condition that is satisfied here, and is called the cancellation condition. Okay. U1 plus U2, U1 V1 plus U2 V2, its class of equivalence, by definition, is U1 plus U2 V1 plus V2. By definition. That's how I add. Okay. The class of 0, 0, I call it simply 0. the class of 0, 0, I call it simply 0. Very good. So let me, before I do this, I need to do something before that. First of all, I need to show that this is an equivalence relation. That is the point. Please write it down. We need to show that this is an equivalent relation. What does it mean, equivalence relation? It must have 3 properties. Everything must be equivalent to itself. If something is equivalent to another, then this other is equivalent to this also, of this. And something is equivalent to another, and this another is equivalent to something third, then the first must be equivalent to the third. These are conditions you cannot avoid. So let us try to understand which conditions are possible. First, UV is equivalent to UV. Just put it here and you will see it. An element is equivalent to itself. True or not? U plus V is U plus V. Come on. That's true. Obvious. Then, if UV is equivalent to U1 V1 to U2 V2, then U2 V2 is equivalent to U1 V1. Obvious, because here the order is not important, and this was mentioned before. So the first 2 conditions are obvious, are obviously true. Now the third condition, and here we get some condition. U1 V1 equivalent to U2 V2, which is equivalent to U3 V3, then U1 V1, it is called transitivity, is equivalent to U3 V3. That's what I need to check. And this is not always true. You have to have some condition. In our situation, it is true. Okay, let me translate. This means that U1 plus V2 is U2 plus V1. This means that U2 plus V3 equals U3 plus V2. Add them up. Add this to this, and it is going to be equal to this plus this. Correct? U1 plus V2 plus U2 plus V3 is equal to U2 plus V1 plus U3 plus V2. What do I see? I see that V2 is present here and here, and U2 is present here and here. I'm tempted to cancel them. But what does it mean, cancellation usually? You subtract, but you cannot subtract. Correct? So you need the following cancellation condition. U1 plus V equals U2 plus V, then U1 equals U2. It is a cancellation condition, and it has to be verified. And I suggest that we do it at home. So for our set, or our semi-group of convex sets, this condition is indeed satisfied. It is a small lemma. You simply prove it straightforward, but you have to prove it.
The problem with cancellation is, I was just thinking that, like, if you took, say, like a square in the upper right quadrant, okay, And you can think about multiplying the vectors representing that square by negative, and so you put it into the lower left quadrant.
Yes.
Okay, so you can think about subtraction, but the thing is that you're
It
gonna
won't
get-
go. You won't. Very good. Actually, I understand. You see, you could consider minus u to be minus 1 times u. That means multiply all elements by minus. But unfortunately, minus u plus u will not be 0.
It's not.
No, no.
Point. Is that the problem?
Yes. Yes, yes, yes. It is not a single point. That's the problem. Simply using
Convex holes in the combination.
yes. But that is definitely, this is the first thing that comes into mind. How do I subtract? I must first understand what is minus u. Minus u is minus 1 multiplied by u. It is a natural. Unfortunately, it does not bode well with our addition. That's why we have to do this Grothendieck group. Otherwise, you cannot introduce. So,
Was this the context in which he introduced the K-functor?
no, well, he definitely had this in mind, but he had a lot of things in mind. What he had in mind was maybe if you have bundles over the same manifold, then you can add them. Simply at each point you take the direct sum of two fibers. But he wanted to make a group out of it. This is called the Grothendieck K group. And in terms of this K group, he was, Atiyah was able to formulate and prove the famous elliptic index theorem. It was exactly in terms of this group. And this is one of the most important objects in modern, say, mathematics, in topology, in differential equations, wherever. But Grothendieck, I think, was mostly, at least Atiyah was motivated by this. There's a nice book by Atiyah of, say, 62, 63, called K-theory, one of the best books on the subject. And Atiyah was motivated by this. But again, I suggest that you look at this and prove it. And after you prove it, you are done, because here you are allowed to cancel V2. Correct? Then you are allowed to cancel U2, and you get exactly what you wanted. So the important thing to understand is this Grothendieck construction allows you to embed a semigroup with one condition. And what is this condition? Cancellation condition into a group. Sometimes the cancellation condition is not satisfied. Sorry, in this case you cannot embed this way, because this condition, this relation is not a equivalence relation. Okay, so let me then again give you another homework assignment. Prove that the Grothendieck group is a group, a commutative group. Moreover, it is even a linear space. What do I need to prove that in order to show that it is a linear space? We need to learn to what? Multiply by, it is a real linear space, by real numbers. Easy. Lambda u minus v, by definition, is lambda u minus lambda v, where lambda is the homothency. Now I have no difficulty understanding what is here. Now I can, by the way, take lambda to be negative. Here, if it is negative, simply I switch u and v. And easy to prove that this is indeed a linear space. Oh, we've got a linear space. Starting from the convex bodies, we switched to the space of equivalence classes of pairs of convex bodies, and this happens to be a linear space. Wonderful, because now I'm going to something very interesting and very important. Let me denote W's, elements of the Grothendieck group. But to say Grothendieck's linear space. So W is a pair, is an equivalence plus class of a pair. In particular, usual convex bodies are part of this. Because how do I embed convex into here? I take U and send it, for example, to U0, to the class of equivalence class. I embed it, correct? Well, now I want to do something quite wonderful. The next step is Minkowski's mixed volumes. Something very important. Again, it should be taught in undergraduate math, but it is not. Very important notion and a real beauty. Let V1, okay, let V be a convex set. By the way, all convex sets are supposed to be compact. I did not mention that, but conv n consists of compact sets. So they do not extend to infinity. Then we understand what is the volume of this body. It is a number. Very good. I want to introduce an n-linear form on this linear space related to the volume. Okay? Vn of W1, W2 is a form, and it will be fully defined just a moment, with the following properties. It is linear in each argument. That means to any, say, n tuple of elements of the K group, we associate a number. And this association is linear in every argument. We understand what does it mean to add two elements of the K group with coefficients. Yes, we do. And so we want it to be linear in every argument. Secondly, we want it to be symmetric. If I switch any two of them, the result does not change. Hmm?
Symmetric or anti-symmetric?
Symmetric. Symmetric. It is symmetric. And third, I want Vn of V be volume N of V. If all arguments are the same, I want it to be the volume. Yes, I want it to be the volume. Claim these three conditions fully define this form. These three conditions fully define this form. I will prove it for n equal 2, and you will immediately understand why this is. Actually, you all know this since, say, senior kindergarten, but maybe in different terms. Yes?
Is V belongs to what? Oh, and there, does V belong to?
V belongs. They all belong to. Okay. V belongs to conv, only to part of it. But because of linearity, this element is a difference of 2. Correct? And because of linearity, it is enough to do it only for V in conv, not for W. Let me show you. It is easy again, it is kids' game. And it is much more. Imagine that I have x, y in a linear space. And I have a bilinear form, linear in both, symmetric, and I know the value for any z. Then I know the form for an obvious reason. Phi of xy is phi of x plus y minus phi of xx minus phi of yy, and I think over 2, if I'm not mistaken. You check it immediately. Because of linearity, this is what? It is phi of xx, cancels, plus phi of yy, cancels, plus phi of xy, plus phi of yx. But phi of xy equals phi of yx, so I get 2 phi of xy, divided by 2, I'm done. It is called polarization identity. And such a polarization identity exists for every number n, 2, 3, 4, 25, whatever. Okay? So, if V1, V2, Vn are convex bodies, that means they are in particular embedded into the Grothendieck's group, correct? Then Vn small of V1 capital, Vn capital is called the Minkowski mixed volume. Minkowski mixed volume. Definitely one needs to have an example. Because physicists without examples become mad. Let me give you an example. Let us consider two-dimensional example. Who knows more dimension than 2? Nobody knows. Yes. And what are your favorite convex bodies? Circle. And what else? Another one. And a square. It is a circle and a square. What is V2 of circle and square? It is volume of circle plus square, circle, okay, it is simply this, minus V of circle minus V of square over 2. We know this. V means, in this case, the area. It is pi r squared. We know this, what is 4r squared, 2r to r. Unfortunately, C plus circle plus square is not very beautiful, is something not very beautiful, but we can draw it. It is going to be something like, it is not a circle, but something like this. Not a big deal to compute its area, correct? And that's what you get. That's what you get. Do you like it? Or what? This is called the mixed volume of the pair circle square. It is symmetric. The order of circle square is not important, but it is a number. Kushnirenko-Bernstein's theorem. The number of solutions of a system of n polynomial equations with n complex variables is equal to the mixed volume of their Newton Polyhedra.
Why is it an integer?
It is. I will say, again, I ran out of time, but that's what I was expecting. But nevertheless, now we know the answer. It's obvious. If you look at it in the, if you look at it, no, the thing is,
That part of the tablet got me.
it was simply they were robbers of, they took it away and published it many years after. But isn't it a real beauty? It started a completely new mathematics, and one of the main contributors, Askol Chovansky, who is currently at, he was also a student of Arnold, he is currently at the University of Toronto. He got a very nice name for this field of mathematics. It is called geometry of formulas. He introduced it as a theory of phenomials, not polynomials, but phenomials. Phenomials, because you see what these Newton polyhedra are about. Actually, you know that there are not many monomials in your polynomial. You see, if there are many, and that's why he called them phenomials. If you start to deal with next time I will simply explain, following Gelfand, why this is obvious. I can just give some hint why this is. No, it is possible to explain. You see, consider several polynomials and consider their Newton polyhedra. And to this set of polyhedra associate the number of solutions. So to a string of convex polyhedra, you associate the number of solutions. That's it. Try to understand what are the properties of this association. You can prove that it is linear in every Newton polyhedra. It is not a big deal to prove it. And you can prove that if all polyhedra are the same, you get simply the volume. And definitely it is symmetric with respect to all polyhedra, because it doesn't matter in which order I take polyhedra, but there is only one. These conditions define the volume in a unique way. And that's what Gelfand understood simply listening to the talk. Said, come on, there cannot be anything else but this. And again, the fact that it is linear. So we have to check, instead of this Vn, we have the number of solutions of the system of equations where W1, W2, Wn are Newton polyhedra. Okay? And let us simply check that this number of solutions satisfies these conditions. Then it must be this. Nothing to do about it. Because these conditions define this function uniquely. So actually, to sum up, today we've learned a number of important things. The general idea of a Newton polynomial, the idea of the semigroup of convex bodies, the idea of Grothendieck's group, and we formulated the theorem, and even actually I have explained how to prove it. What is left is just to actually check it, which is not a big deal. Modulo some details. Modulo some details. Details are not very bad, but they're easily done by any reasonable, say, math professional. Okay. Okay, that's it. Thank you.